Welcome to problem number 5, I presume, on problem number 5 of Blind 75. And this problem is called top k elements in a list. So generally speaking, this problem gives us an array of numbers and an integer. The array of numbers contains uh, a list of numbers with around 6 values in it, give or take, or it could be more than that, but it should be restricted within this problem to around 6 values. And within those 6 values, many of the numbers are repeated numbers. What I mean is that we'll have one twice, maybe we'll have three a couple of times as well, maybe we'll have four once, and some other number once, right? So we'll have numbers that might be repeating more than once. And the target of this particular problem is that we need to, once given an array, as you can see, this array that we can see here, once given an array and a target number, the target number basically tells us, hey, give me the top two numbers which are repeated the most in that array. And if you look at this array in this example here, we have one once, so we can write down one once. Then we have two times. We write down two times. And then we have three times. Three times. When we have this number, now we need to return array of rather a list of numbers, if you're referring to Python, which has two values, and those two values are the most repeated numbers based on the input, which is the target given to us, which is k equals to, let me start a little unclear, so let's make it a little more clear. K equals to 2. Based on that, we need to find two numbers from this which are repeated the most. Number 3 is the most repeated number, so we select this as number 1, and number 2 is the second most repeated, so this is the second number that we select, right? And keep in mind, we can return these numbers in any order. Focus on this word here. So we don't need to focus on the numbers being ascending or descending order. All our focus in a logic is A. We find out the frequency of all of these. We find out all the different numbers in the array given to us. Then we look at the frequency of each given number. And then we identify based on the amount given and the value given us in the K. Based on that, we select the top k number of elements from repeated elements from that list. So that is, generally speaking, all we need to do in this particular problem. It sounds easy enough, but there again, the logic is something that you need to internalize before you actually are able to solve this, because practically when you're in a coding interview, you would not have, again, most people don't have it on the top of their heads which libraries to use to get the answer. So generally speaking, you might want to solve these problems from a more logical standpoint rather than a root memorization standpoint. There are two methods to solve this problem, as previously mentioned, and we're going to go over basically both of them. The first one is more so a very, very short, sweet solution, but it is not as efficient as the other solution, right? But at the same time, another drawback of this first solution, even though if it's very, very short and easy to write down, is that it is, it is basically very counterintuitive to understand, because we use uh, functions more than, we use functions to solve this. The first solution uses functions and libraries to solve this problem. That's why we can solve this problem in 2 lines instead of the many in the second solution. But at the same time, the second solution is more important because that is a logic-based solution where you'll need to build your logic out for this problem first before you can solve this problem. Let's move on to the first solution, which is using libraries. So generally speaking, we can break down the steps again to three things: count number of frequencies, how often an element appears in the list. We sort by frequencies, and then we sort these elements based on their frequencies in descending order, and then we select the top k elements and return them in an array. To implement the first solution efficiently, we use the collections.counter class to count the element frequencies and heap q.nlargest to extract the top k elements by frequency. So again, we're using two libraries and custom data types to basically set this up. So first, we're going to import both of the libraries here. So first thing, let's go back to the code here. Yeah, we've already imported that actually. So from collections, we import counter, and we import heap q library basically. After that, we have step one, where we count the frequency of each element. And I'm not typing this down because this is more so just, two lines of code, and these two lines of code are just overly relying on existing, libraries and custom data types to solve this problem. So we count the libraries using the counter custom data type from the collections library. And then we use heapq to find the k elements with the highest frequency. So heapq.nlargest is the function. Then we put in the arguments k count.keys and key count.get. A little breakdown of this, I think this particular data structure might be needed. So let's break this down a little bit, right? So basically, heap q.nlargest's key components are: the first value in the argument is the n, which we in this case would be k, which is basically the largest numbers you want to return from an iterable, right? That is the value that the top 2 or 3 values that you want to result from whatever value you have. Then we have count.keys, which is the iterable. These are the values that we want to go over one by one. Those are the keys. And then we define the key. The key for this is count.get, right? And basically, what count.get is, to be more specific, it is a parameter that tells us the function to rank the elements not by their natural order, but by their associated frequency and count. The count.get function basically retrieves the frequency value of each element, and this frequency is used to determine which element is the largest. With that out of the way, I think we have some clarity on how this function works. And again, like, I don't want to put too much time in this particular solution and method for this problem, because again, like, this is more so of a quick, easy solution. In 2 lines using libraries, you can get this done and solve this problem. And this could also be considered one of the memorization techniques to solve these solutions that you might just remember and hope that might come in. But again, I wouldn't recommend that at all. But again, if even you can use this more so logically as well, if you're able to understand these inherent libraries and remember their use cases without looking up documentation, which is probably not that easy to do, because most programmers, even at high levels, don't remember libraries. They just look up documentations, and based on that, they create the solutions. They don't remember these libraries in question unless you don't use them a lot in their day-to-day tasks. So when we talk about the time complexity of the solution, or even though it's efficient, it is not that efficient. It is basically, the time complexity is O(n) log k, right? So it's not more efficient, it's less efficient, and it's counterintuitive, but it gets the job done basically. That's where we put a stopping point on this solution. So with that out of the way, what is the most logical way to solve this problem, right? So let's get this code out, or rather, I think we didn't test this code out. So yeah, before we move to that solution, let's test this out as well. Let's run this code, and it should solve the problem. Yeah, both cases were solved properly, and this code works basically. Again, like, I wouldn't recommend this, but if you want a quick, easy solution to this problem, this was the quick solution. Now, with that out of the way, what is the more logical, deliberative solution to this problem? let me bring this to the top right now, because, or rather, let me just come to the empty space and explain this in a way that we can get this out of the way. So there's some algorithm before we move on to the specifics of the method, second method, the more logical method. Let's first understand the core crux of what we'll be covering here. A lot of you might be familiar with bucket sort, right? Uh, if you are not familiar with that and you have read statistics at some point in your life, you'll be familiar with what buckets are in statistical aspect. But even if you're not familiar with that, let's just basically quickly just treat. So let's say that we have buckets, different buckets, right? As you can see, I'm using the green pointer to create these different buckets, right? And my drawing skills are less than exemplary, so please don't mind them. So with that, we have three buckets, let's say, right? And we have three values here. Let's say one. Let me not use this color here. Let's just use the other one. We have one. We have two. And we have three. What this does is basically it counts how many ones every time it inquire. Let's say we have a array which has, let's say, 1 comma 1 comma 2 comma 3 comma 3. So we have, let's say, an array with 5 numbers, 2 ones, 1 2, 2 threes, right? So a bucket sort, what it does is it goes over, let's say it's iterating over this iterable, right? So it sees one, oh, it's one. So it goes there, drops that in this bucket, and moves on to the next one. Oh, this one's also one. So it takes that down the same route and drops that into the one bucket again. And the value in the one bucket becomes 2. So there are 2 values within the one bucket that are 1, basically. So that's the frequency of 1, right? And I think you're probably dot connecting here in understanding how this could help in this particular problem. It's counting the frequencies by arranging items in an array in buckets, right? Similarly, we have 1 2. So it takes that 2, it brings it down here and drops that into the 2 bucket. And there's just one value with 2 in it, so we write 1 here. And similarly, it goes to 3 and drops that into the 3 bucket, right? Similarly, it does that for both of them, and we have 2 here, right? So that is what a bucket sort is generally. But the issue with bucket sort is going to be a major one if we move down this path. Let me just clear all of this here. Let's clear this out. Let's clear this thing, this list. Yeah, let's just clear this list out as well. So we get the pen back here. So let's create another array, right? Let's say we have values 1, 2, 5, and 100, 7, and 100. Doesn't seem that bad, right? And the reason I'm going over this is that you need to understand a major limitation of bucket sort and understand that this problem is not that easy, logically speaking, right? So if we do bucket sort with that, we'll need to create 100 different buckets here, because we can't create buckets for 1, 2, 5, and 7, and 100. What bucket sort means, it creates buckets for across the spectrum here. So from here to here, the lowest to the highest value, bucket sort will create a, bucket sort would create all buckets there, and then count for every bucket from on the algorithm, right? It goes over, looks for all ones, adds them to the one bucket, and it goes through, looks for all twos, adds them on the bucket, so on and so forth, right? Presumably, if it wasn't 100, the last item was 100. Let's say, uh, let's say it became let me just remove this portion here. Yeah, let's say it became 1 million, right? 1 million. 3, 4, 5, and 6. Now, your computer would have to create 1 million different buckets. You see where how that problem goes long, how it creates and consumes so many different resources that you might not want to, or your computer might not want to do that, or it would become a very, very inefficient way to do that, right? And the reason I'm going through this, because this is the sort of logic most coding interviewers will be looking for when you work on your on this problem solution. The other solution might be easier, might be memorable, but that solution would not be something that most of the coding interviewers are looking for, right? So we have a million different buckets that we might have to create at this point, and that seems very, 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 very stupid way of solving this problem, because it just destroys the purpose of being efficient, right? It's better than you just use method one instead of doing that. So how do we resolve this problem in bucket sort? And that is not that difficult as well. So generally speaking, we have buckets of all numbers, and all numbers being added on top of that, right? That's how we're doing. What if we decide, hey, let's not have buckets from 1 to 1 million. Let's create buckets based on every item in the in the bucket sort algorithm, right? So that is a way we can potentially do that, right? So we create buckets for all values within this within this within this array. So 1, 2, 5, 7, and 1 million, right? And then we potentially track all of those values, and that just limits us to just 5 buckets basically. So that is what we intend to do with bucket sort. So with that out of the way, let's just drag ourselves back to the main problem at hand, right? Let's go back to the problem that we need to cover first. Yep, here we are. Let's open the pen again. And now let's focus on how we're going to solve this problem with bucket sort, right? So let's move to the key insights that we need to have before moving. You need to understand the maximum frequency of any element is limited by the length of the array, right? And since an element can appear at most n times, we can create n plus 1 buckets where the index of each bucket represents the frequency of elements. So how many elements? So that's the point. I think I didn't explain that clearly. Let me just go back to the screen here. So instead of having like buckets from 1 to 1 million, what we do is we have 6 elements in the list, right? That's basically our main issue, right? So we create 6 buckets, just 6 buckets. I'm not going to draw the complete buckets. I'm just drawing the circles to represent buckets. We know at all times there are going to be 6 elements in a list, right? So we just, based on that, create 6 buckets of all the elements in the list. And we just create the buckets amount with frequencies. So it appears 1 time, it appears 2 times, it appears 3 times, right? So on and so forth. The buckets don't represent the items. The buckets instead represent the value, right, of how many times that particular item repeated itself. So once we have that, we know the buckets are always going to be constrained to a certain value, which is 6, the amount of elements in the list. So with that, let's move back to the question at hand. With that, let's move on the steps on how we're going to solve that out. And then I'll add my pseudocode. And as always, we're going to code the problem out and see if it solves the problem. So first, we're going to count the frequencies of how many times each element appeared in the input list. Then we bucket the elements, create an array of buckets where we create 8 bucket at index 1 contains elements that appears exactly I times. Then we collect the top of the k elements with the highest frequency bucket, collect the most frequent elements until we have k elements left. All right, let's start basically. So again, I think collections is a very, very useful library. So, and I use it a lot. So I would be using the collections library to a large degree. So let me just import collections and counter from that. From collections, import counter. So with that out of the way, let's paste our pseudocode. Step one is to count the frequency of the elements. So again, we're going to leverage the collections library's counter algorithm and just create a variable based on that. So count so count equals to counter, and the argument is nums. Then we look at the second pseudo code that we have sorted out for this, copy that and paste it here. And again, like pseudocode is helps in writing your steps in English, and then you can convert that English and translate that into, simply speaking, you can translate those steps into uh, into Python code, right? So we create the buckets where index is the frequency and values are the elements with that frequency, right? So we create the length of the, we take the length to first create the bucket, no understand how many buckets we're going to create. So n equals to len of simply the number of elements in the array, and then we basically create the buckets based on that. So for buckets, we create buckets. Then we write down the code for that. We're just going to use list comprehension. So we're creating lists here, empty lists for, we're just using underscore as the iterable here in range of n+1. We're using n+1 because the length of items and +1, we, we create an additional column with just z of which records, 0 basically. So with that out of the way, let's get our next pseudocode paste it here, the next step, if you will. Then we fill in the buckets. The next step is we fill in the buckets with the elements based on their frequency, and then we write down the code for that. So the next step was going to be we need to fill in the buckets with elements based on their frequency. So let me write down that code. So for num freq in count.items, we're going to create a for loop. Yep, I'm sorting out the code, thinking it through, and then we just append the frequency value that we determine uh, 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 into the basically within the frequency key, within the frequency of buckets, we append the value of num within that. So buckets frec, which is the frequency, dot append nums, or rather it's num, my bad. Then we have step 3. Step 3 is basically collecting the top k elements from each element, and we're not just going to use the heap q library here. Instead, we're going to do this manually, where we can understand our logic. So then we create an empty list called result. Then we get our next piece of pseudocode in. Again, pseudocodes just help make sure that I'm on the correct track. So I just like to use them wherever I can. And I would recommend you do the same. So then we have a for loop for I in range n comma 0 comma -1. -1 means that we're taking negative steps from the highest to the lowest. Then we write down the control structures for this. If buckets I, then result.extend buckets I. And then the second if statement, if len results is greater than equal to k, we return the spliced result of that. And with that, that should complete our, our code on this problem. So let's just break this down a little bit as well. We have the counter nums counting the value. We have the buckets equals to empty list for underscore range in n+1. We create empty buckets where n is the length of the input list. Each index I in buckets represent the frequency, and list at the index stores all the elements appears in I. We fill in the buckets by iterating over the count dictionary, append each element to the bucket in the corresponding value. We collect the top k buckets and we exit early once we have collected k elements and we return, right? So with that, let's just test this code out. Let's see. Oh, yeah, definitely syntax issue. Let me check. Yep, here it is. Let's fix that. Let's try again. Yep, and all of the cases are working as expected. So that's the more logical and correct way to solve this problem, not a quick solution that you might just want to use, but correct and logical way to solve this problem. So generally speaking, time frequency for this is divided into the 3 steps that you could see in my code, pseudocode. In step A, when we're counting, step 1, when we're counting frequencies, it takes O of n, which is depending on the length of the input list. In bucketing the elements, it also depends. The time complexity is also O of n, and collecting the top k elements in the worst case scenario, we iterate over all the buckets, which again is O of n. So the overall time complexity of this O of n, this means that it's a very, very efficient approach for large input sizes in regards to this algorithm. And this would be probably the best solution that you can place when solving this problem. So with that, we'll wrap up this fifth problem on arrays and hashes of blind 75. And we'll see you in our, when we are solving the next problem. Thank you.